Buffalo Harbor, autumn, 1842. The air was thick with the smell of rotting wheat, and ships were locked in a gridlock that would last weeks. 2 million bushels sat trapped in ship holds, while Joseph Dart watched his profits evaporate into the October air. His competitors laughed when he proposed the solution, calling it Dart's folly, the steam bucket contraption that would never work. 4 weeks later, not one of them was laughing. They were scrambling to survive. The numbers told the crisis in stark terms. By 1832, Buffalo's grain receipts had exploded to 2 million bushels annually. The Erie Canal had delivered on its promise, dropping shipping costs to a tenth of what wagon transport charged. Grain from the interior flooded eastward in quantities nobody had imagined possible. The canal connected the Great Lakes to the Hudson River, linking the agricultural heartland to the eastern cities that consumed its harvest. But the canal had solved only half the problem. The wheat sat in ship holds, waiting. Stevedores worked around the clock, their backs bent under sacks weighing 120 pounds, their muscles straining against block and tackle systems that had not changed in centuries. Unloading a single vessel took a week or more. Teams descended into dark holds, shoveling grain into sacks, hoisting them by rope and pulley to the deck, then carrying them across gangplanks to waiting canal boats. Every bushel passed through human hands at least twice. Every transfer cost time, labor, and money. The economic threat was existential. The canal had made Buffalo the gateway between the Great Lakes and the eastern seaboard. But the port was drowning in its own success. The canal had made floating grain cheap and efficient. But if it cost more to move grain across a wharf than it did to float it 300 miles, the entire system collapsed. This was the fundamental conflict, biology versus physics. The Midwest could produce grain faster than the human back could lift it. Mechanical reapers were multiplying harvest yields. Better planting techniques were increasing production. The land was giving up more grain every season. Here is the math that kept merchants up at night. A strong stevedore crew could move perhaps 50 bushels per hour if they worked without rest. To handle 2 million bushels in a shipping season meant crews working every single day, dawn to dusk, for months. The bottleneck was not in the canal. It was not in the ships. It was in the 20 feet of space between the ship's hold and the dock. Merchant ships arriving from Chicago and Detroit found themselves anchored in the harbor for days, sometimes weeks, waiting for their turn at the few available docks. Grain that sat too long in poorly ventilated holds began to heat. The heating turned to spoilage. The spoilage turned to total loss. Captains watched their cargo transform from golden wheat to worthless compost while waiting for human hands to move it. Buffalo's warehouse owners scrambled to build more storage facilities. But storage only delayed the inevitable. The grain still had to be moved, sack by sack, back by back. And winter was coming. Once the lakes froze, everything that had not moved by December would sit until spring thaw. The land could grow more than human hands could move. America had unlocked infinite harvest potential. But biology could not keep pace with physics. Something had to break. The trap. The cruel irony was that every other link in the chain had been revolutionized. The Erie Canal itself was an engineering marvel, a man-made river that had conquered the Appalachian Barrier. 363 miles of hand-dug waterway. 83 locks lifting boats over elevation changes. The largest public works project America had ever attempted. It succeeded beyond anyone's imagination. The ships that plied the Great Lakes had grown larger and more efficient every year. Shipbuilders were designing vessels specifically for the grain trade. Hulls were optimized for bulk cargo. Rigging was simplified for faster loading. Maritime technology was advancing rapidly. The farmers in Ohio and Indiana were adopting mechanical reapers that multiplied their harvest capacity. Cyrus McCormick's reaper was spreading across the Midwest. What once took a dozen men with scythes now took 2 men with a machine. The agricultural revolution was happening in real time. But at the waterfront, nothing had changed since ancient Rome. The stevedore's tools were prehistoric. A wooden shovel, a rope, a pulley. The techniques were medieval. Dig into the pile, fill the sack, tie it off, hoist it up, carry it across, dump it, return, repeat. The only variable was how much punishment the human body could endure before it collapsed. Some men lasted decades. Most did not make it 10 years. The economics made no sense. The canal had cut transportation costs by 90%, but those savings evaporated the moment the ship reached Buffalo. The cost of unloading exceeded the cost of the entire voyage from Chicago. Merchants were paying more to move grain 20 feet vertically than to move it 300 miles horizontally. Every calculation pointed to the same conclusion. The bottleneck was killing the entire system, and the stevedores suffered most of all. The work destroyed bodies. Men in their 30s had the backs of men in their 60s. Hernias were common. Crushed fingers were routine. Falls from gangplanks were frequent enough that everyone knew someone who had drowned in the harbor or been crippled by a tumble onto the dock. Medical care was primitive. The workers accepted the injuries as the cost of employment. The profession was a trap. It paid better than factory work because it had to. No one would do it otherwise. But the work was seasonal, dependent on the shipping window. When the lakes froze, the stevedores had no income. When the ice broke in spring, they returned to the same brutal cycle. Some men saved enough to survive the winter. Most went into debt, paying it off during the shipping season, then going into debt again when winter came. This was the world that business depended on, an entire regional economy built on a foundation of human suffering. Everyone accepted it because everyone had always accepted it. This was how grain moved. This was how it had always moved: muscle and rope and time. The methods were ancient, proven, and immutable. The established interest actively resisted change. The stevedore gangs were organized, powerful, and deeply suspicious of anything that threatened their livelihood. They had political connections. They could shut down a dock with a work stoppage. They made it clear that any attempt to replace them would face fierce resistance. The warehouse owners had invested in facilities designed for sack storage. Their buildings had loading docks at specific heights. Their interior spaces were configured for stacked sacks. Their accounting systems tracked inventory by sacks. Changing the fundamental unit of storage would mean rebuilding everything. The insurance companies had policies written around manual handling. They understood the risks of human labor. They knew how to price those risks. A new technology would introduce unknown variables. Unknown variables meant unknown risks. Unknown risks meant higher premiums until the data came in. The entire commercial infrastructure of Buffalo assumed that grain would always move the old way. Changing that would require overturning decades of accumulated practice. The inertia was enormous. This was not just a technological problem. It was a political and economic fortress built to resist innovation. The dormant solution. But the solution had been sitting in a dusty patent archive for 60 years. Newport, Delaware, in the 1780s. Oliver Evans stood in his flour mill, watching water turn a wheel, watching that wheel turn gears, then watching those gears grind wheat into flour. The process worked, but it required constant human intervention. Workers hauling sacks upstairs, dumping grain into hoppers, shoveling flour from one station to the next. Evans saw inefficiency everywhere. He saw men doing what machines could do. He saw muscles where mechanics should be. Evans saw the mill as a single organism, a continuous system where gravity and mechanical advantage could replace muscle entirely. He began sketching designs. He tested mechanisms. He failed. He learned. He tried again. The process took years, but Evans was patient. He understood that the right solution would be worth the effort. The Archimedes screw had lifted water for 2,000 years. A simple helical blade rotating inside a tube pushed liquid upward with each turn. Evans adapted the principle for something nobody had tried before: dry goods. His screw conveyor pushed grain horizontally through an enclosed trough. The rotating helix acted like a screw thread, pushing the grain forward. No shoveling, no carrying, just continuous motion. The grain entered one end and emerged from the other, moved entirely by mechanical force. For vertical movement, he invented the bucket elevator. An endless belt fitted with small cups scooped grain from the bottom, carried it upward, then dumped it at the top by centrifugal force. The physics were elegant. As the buckets rose and passed over the top pulley, the rotation caused the grain to fly outward, dumping into a receiving chute. The buckets descended empty, rose full, and discharged automatically. The system ran as long as the water wheel turned. Evans connected these mechanisms into a production line. Grain entered at ground level, moved horizontally via screw conveyor to the base of a bucket elevator, rose to the upper floor, traveled horizontally again to the millstones, then descended through chutes to the packing station. The entire process required human labor only to start the machinery and collect the finished flour. Everything else happened automatically. The economics were stunning. Evans reduced milling costs by 50%. A mill that once required a dozen workers could operate with 2 or 3. Production speeds doubled, then tripled. The quality improved because the process was consistent. Human error was eliminated. The automated mill represented the first true assembly line in American industry, decades before Henry Ford applied the same principles to automobiles. But the innovation remained dormant. Evans built his mills in the 1780s, but the supporting infrastructure did not exist. Steam power was experimental, expensive, and unreliable. Most mills still relied on water wheels. The flour mills of that era served local markets that did not need to process millions of bushels. A village mill ground enough flour for the surrounding farms. The scale that would justify Evans's system had not arrived yet. His patents expired. His designs gathered dust in technical journals. A few millers adopted his methods, but most stuck with tradition. Evans spent his later years frustrated, watching his innovations ignored by an industry that didn't understand what he had given them. He died in 1819, never seeing his system transform American commerce. He had built the blueprint for the kinetic revolution, but it sat waiting for a problem big enough to demand it. The technology existed. The principles were proven, but the crisis that would force adoption had not arrived yet. That problem arrived 23 years later, in Buffalo Harbor, where 2 million bushels of wheat were rotting in ship holds, while merchants watched their fortunes disappear. The unlikely hero. Joseph Dart was not an engineer. He was not an inventor. He was a merchant, a businessman who watched his profits evaporate in Buffalo's gridlocked harbor. He understood ledgers, not machinery. He knew markets, not mechanics. But he had something more valuable than technical expertise. He had desperation. In 1842, he owned grain. He owned ships. He owned warehouses. But none of it mattered if the wheat could not move from hold to dock to canal boat before it rotted. Every day, his ships sat waiting for unloading was a day of lost capital. Every bushel that spoiled was money thrown into the harbor. The interest on his loans kept accruing. The storage costs kept mounting. The whole operation was bleeding cash. Dart understood the economics better than anyone. He had calculated exactly how much the bottleneck was costing him. The numbers were staggering. He was losing more money to delays than he was making on successful shipments. The business model was broken. If the situation did not change, he would be bankrupt within 2 years. But Dart had read about Oliver Evans. Somewhere in his research into milling operations, he had come across descriptions of the automated flour mill. He understood the principle. Buckets on a belt, powered by steam, lifting grain vertically without human muscle. The concept was elegant. The challenge was scale. Evans had built for flour mills processing hundreds of bushels per day. Buffalo needed to move thousands of bushels per hour. The bucket elevator that worked in a 3-story mill would need to be 10 times larger, 10 times stronger, driven by steam power instead of water wheels. The engineering would be complex, the construction would be expensive, but the alternative was bankruptcy. Dart needed someone who could scale the concept to industrial dimensions. Robert Dunbar was that engineer. Dunbar had experience with steam engines. He understood power transmission. He knew how to calculate the stresses on mechanical systems. Most importantly, he understood that the principles Evans had proven in a flour mill would work just as well in a grain terminal. The physics were the same, only the scale was different. Together, they spent the winter of 1842 to 1843 designing something America had never seen: a mechanical grain elevator, powered by steam, capable of lifting thousands of bushels per hour from ship holds to elevated storage bins. The waterfront laughed when word spread about DART's plan. A steam bucket contraption, that's what they called it. DART's folly. The rich merchant trying to replace men with a machine. The established stevedore companies dismissed it as fantasy. The warehouse owners called it impractical. The competing merchants saw it as desperation. DART was hemorrhaging money, they said, and now he was going to waste even more on a mechanical pipe dream. Their objections seemed reasonable. Grain wasn't like flour. It came in irregular lumps, mixed with chaff and dirt and sometimes rocks. How would buckets handle that? The machinery would clog, the belts would break, the whole thing would collapse under the weight. Evans had worked with processed flour, carefully cleaned and dried. DART wanted to lift raw grain, straight from the ship's hold, damp with lake water and contaminated with debris. And what about the cost? Steam engines were expensive. The construction would require massive timbers, iron fittings, precision metalwork. DART would bankrupt himself building this monument to his own arrogance. Meanwhile, the old way kept working. Slow, yes. Expensive, yes. But reliable. The stevedores might complain about the work, but they showed up every day. They moved the grain. The system functioned. The stevedore gang saw it as an existential threat. If DART's machine worked, they were finished. Hundreds of men would lose their livelihoods overnight. The gangs had families. They had debts. They had no other skills that could match the wages they earned on the docks. The resistance was fierce and vocal. Some threatened sabotage. Others lobbied the harbor master to deny DART a building permit. They argued that the steam engine would be a fire hazard. They claimed the structure would block ship traffic. The mockery had an edge of fear to it, because everyone understood that if DART succeeded, everything changed. The fortunes built on manual labor would evaporate. The carefully constructed political alliances would become worthless. The world they knew would end. The men who controlled Buffalo's waterfront would lose their power overnight. So they laughed. They called it impossible. They predicted spectacular failure. They spread rumors that DART was mentally unstable, throwing good money after bad. And they waited for DART to prove them right. They expected to watch the construction fail, the machine break, and DART sink into bankruptcy. Then, things would return to normal. But DART and Dunbar were not deterred. Through the brutal winter of 1842 to 1843, they built. The structure rose above the waterfront. It was 50 feet wide, 100 feet long, and it rose 30 feet above the dock. A wooden skeleton filled with mechanical ambition. Inside, a steam-powered engine drove a continuous belt fitted with iron buckets. The marine leg, a movable arm that could be lowered into ship holds, extended from the building. The whole apparatus looked alien, industrial, nothing like the traditional warehouses that lined the harbor. The engineering challenges were immense. The buckets had to be strong enough to carry wet, heavy grain, but light enough that the belt could move them efficiently. Dunbar calculated the loads carefully. Too heavy, and the steam engine could not drive the system. Too light, and the buckets would bend under the weight of the grain. He settled on iron buckets, each one about 6 inches deep, spaced on 2 feet apart on the belt. The spacing had to be precise, close enough to move grain efficiently but far enough apart that they would not jam when they rounded the pulleys. The discharge mechanism had to dump the grain cleanly without clogging. Dunbar designed a curved hood at the top of the elevator. As the buckets passed over the drive pulley, the curve caused them to tip, dumping their contents into a receiving chute. The grain fell into elevated storage bins, while the empty buckets descended to scoop another load. The belt itself was a challenge. Leather belts would rot from constant contact with damp grain. Canvas would wear through too quickly. Dunbar used a combination of canvas reinforced with metal plates at stress points. The belt had to be flexible enough to bend around the pulleys, but strong enough to handle the weight without stretching or breaking. The steam engine was the heart of the system. It drove the belt with consistent power, hour after hour, without fatigue. No breaks for lunch. No stopping when muscles gave out. Just relentless, mechanical motion. Dunbar connected the engine to the drive pulley through a series of gears that controlled the speed. Too fast, and the buckets would spill grain. Too slow, and the system would not achieve the throughput Dart needed. By May of 1843, the facility was ready. Dart had invested everything. His warehouses were mortgaged. His ships were pledged as collateral. He had borrowed from every bank that would lend to him. If this failed, he was ruined. His competitors would divide his assets. His family would lose everything. But if it succeeded, he would own Buffalo. The risk was total. The potential reward was absolute dominance. The proof. June 1st, 1843. The first test run. A grain ship pulled alongside Dart's elevator. The captain, skeptical but curious, agreed to be the guinea pig. The waterfront crowded with spectators. Competing merchants stood with arms crossed, waiting to see the failure. Stevedore gang leaders watched with barely concealed hostility. Harbor officials took notes for their reports. Everyone wanted to see Dart's folly in action. The marine leg descended into the hold. The mechanism was crude, but functional. Workers guided it into position. The steam engine fired. The belt began to move. The buckets dipped into the grain, scooped up their load, and began the climb. The first few minutes were tense. Would the belt hold? Would the buckets clog? Would the discharge mechanism work? The grain rose 30 feet. The buckets tipped at the top. The grain fell into the receiving bin. The buckets descended empty. They scooped again. The cycle continued. 600 bushels per hour. The watching crowd went silent. That number meant everything. The fastest stevedore crew in Buffalo could move perhaps 60 bushels per hour if they worked without rest. Dart's machine was 10 times faster. It never tired. It never slowed. It never demanded wages or breaks or water. It just ran, bucket after bucket, hour after hour. What had taken a crew a week now took hours. A ship that would have waited days for an unloading berth could discharge its cargo and return to the lakes the same day. The captain calculated the savings immediately. Less time in port meant more trips per season. More trips meant more profit. He would use Dart's elevator every time. By the end of the first year, the system guy was handling 2,000 bushels per hour. The improvements came from small adjustments. Dunbar redesigned the buckets with a slight lip that held more grain. He optimized the belt speed to match the discharge rate. He added a second marine leg so 2 ships could unload simultaneously. The fundamental principle was proven beyond any doubt. The merchants who had mocked Dart stopped laughing. They started calculating. If Dart could turn ships around in hours while they took days, he would capture every shipment. Captains would prefer his facility because it meant less waiting, less spoilage, faster payment. Word was already spreading across the Great Lakes. The ships would come to Dart first. The old warehouses would get whatever was left. Dart wouldn't just win, he would monopolize. The mathematics of competition had changed overnight. The manual system could not compete with the mechanical one. It was like watching a man race a locomotive. The outcome was never in doubt. The flood. The transformation was not gradual. It was catastrophic for the old order. Within 2 years, competing elevators rose along the waterfront. Other merchants watched DART's success, with the desperation of men watching their businesses die. They had no choice: build an elevator or lose everything. The economics were brutal and simple. DART was capturing 90% of the incoming ships. The remaining 10% were not enough to keep a business solvent. Robert Dunbar became the most sought-after engineer in Buffalo. He designed elevator after elevator, each one learning from the last. The second generation was more efficient than the first. He improved the marine leg mechanism, making it faster to position. He refined the bucket design, increasing capacity by 20%. The third generation was more efficient than the second. He added mechanical sorting systems that separated grain by quality as it flowed through the elevator. The technology improved with terrifying speed. By 1860, Buffalo operated 10 major grain elevators, with combined storage capacity exceeding 1.55 million bushels. The city that had nearly drowned in grain now processed it faster than the Midwest could grow it. The bottleneck was gone. Ships arrived, unloaded in hours, and departed. The harbor that had been choked with waiting vessels was now clear. The efficiency was almost shocking. The stevedores were destroyed. Not slowly, not gradually, but within a season. Gangs that had controlled the waterfront for decades found themselves obsolete. The first elevator put 100 men out of work. The second elevator put another 100 out of work. By the time the 10th elevator was operational, the profession had essentially disappeared from Buffalo. Some men tried to adapt, becoming machine operators. The work was easier but paid less. Most simply disappeared, moving to other ports where manual labor still ruled, or leaving the docks entirely for factory work. The architectural impact matched the economic one. The grain elevator emerged as a new building type. These were not warehouses in any traditional sense. They were tall, functional structures defined entirely by their mechanical purpose. Vertical storage bins stacked like columns. The marine leg extended like an arm into the water. The constant hum of steam engines. The smell of grain dust in the air. These were machines you could walk inside. The buildings dominated the skyline. They were taller than any church, more imposing than any mansion. They represented the new industrial order, where function dictated form and efficiency was the only beauty that mattered. European architects would later study Buffalo's grain elevators as examples of pure industrial design, freed from decorative tradition. By 1865, Buffalo operated 26 grain elevators. The city had surpassed London, Odessa, and Rotterdam to become the world's largest grain port, handling over 7 million barrels of wheat and flour annually. The Erie Canal had created the opportunity, connecting the interior to the coast, but DART's elevator made it real. The infrastructure could finally handle the volume that the canal delivered. The transformation was complete. The city that had nearly strangled on its own success was now the unchallenged grain capital of America. The ships came from Chicago, Detroit, Milwaukee, and Cleveland, all of them carrying grain that would flow through mechanical elevators at speeds that would have seemed impossible just 20 years earlier. The innovation changed more than throughput numbers. It changed the nature of the commodity itself. Grain was no longer measured in sacks as discrete countable units that men carried. It was measured in volume, in bushels per hour, in the continuous flow of material through mechanical systems. The elevator did not just move grain faster. It transformed grain from a solid into a fluid, from something that sat in piles into something that streamed through pipes and chutes. This was the true revolution. This philosophical shift rippled through the entire agricultural economy. Farmers began thinking of their harvest differently. They sold grain by the bushel, but they thought of it as flow. How many bushels per hour could they deliver? Railroads designed cars for bulk flow rather than sacks. They built hoppers that could dump their entire load quickly. Markets priced grain by volume rather than weight. The entire conceptual framework of agriculture changed because of how the grain moved. The new building type changed architecture permanently. The grain elevator's vertical bins became the model for industrial storage worldwide. Concrete silos for cement, steel tanks for oil, refrigerated towers for frozen goods, all of them descendants of Dart's wooden elevator. The principle of vertical storage with mechanical flow became universal. Dart had solved the vertical problem. Grain could now rise from ship holds to storage bins without human intervention. This single innovation unlocked the Erie Canal's full potential. The cost savings that had been promised by the canal's builders finally materialized. Shipping grain from Chicago to New York became cheaper than anyone had imagined possible. The economic geography of America shifted. Buffalo became wealthy. The farmers of the Midwest gained access to Eastern markets. The cities of the East gained affordable food. The consequences cascaded through the economy. Cheaper bread meant urban populations could afford better nutrition. Better nutrition meant healthier workers. Healthier workers meant more productive factories. The Industrial Revolution in the East was fed by grain that flowed through Dart's invention. You could draw a direct line from the mechanical elevator to the rise of American industrial power, but the human cost was real. The stevedore profession essentially disappeared. Thousands of men who had made their living with their backs found themselves obsolete. Some adapted. Most did not. The efficiency that fed millions displaced hundreds. This was the bargain of mechanization, repeated across every industry, in every generation. The gain in productivity came with a loss in employment. Society as a whole benefited. Individual workers suffered. Today, every grain terminal in the world traces its lineage back to the wooden structure Joseph Dart and Robert Dunbar built on the Buffalo waterfront in 1843. The technology has evolved. Steel replaced wood. Electric motors replaced steam engines. Computer systems control the flow with precision Dart could not have imagined. Sensors monitor moisture content, temperature, and quality. Automated systems route grain to specific bins based on grade and destination. But the fundamental principle remains unchanged. Buckets on a continuous belt lift grain vertically, discharge it automatically, turning solid into liquid. The modern farmer in Kansas harvests wheat that flows through a system Dart would recognize. The combine auger leads to the grain cart. The grain cart leads to the truck. The truck leads to the elevator. The elevator leads to the barge or rail car. Every link is mechanized. Every transfer is automatic. The shovel remains in the barn, a relic of an era when human muscle was the only force available to move the harvest. Dart proved something profound. The obstacle that everyone accepted as permanent was actually just a problem waiting for someone desperate enough to solve it. He was not the smartest man in Buffalo. He was not the most technically skilled. Robert Dunbar deserves equal credit for the engineering. But Dart was the one who refused to accept that his business had to fail because human hands could not move grain fast enough. He looked at an impossible problem and decided it was merely difficult. The competitors who laughed at his steam bucket contraption spent the rest of their careers trying to catch up. Most never did. The month after Dart's elevator went operational, the balance of power in Buffalo shifted permanently. Dart did not just gain market share, he redefined what market dominance meant. The men who adapted survived. The men who clung to the old ways disappeared. This is the pattern that repeats throughout industrial history. The innovation that seems ridiculous becomes the standard everyone must adopt or die. Subscribe to see more stories of the machines that everyone mocked before they changed everything.